welcome grade 12s. Today is the last lesson that we're looking at organic molecules in terms of theory. So we've done 3. The first one we looked, well, 2 before today. The first one we looked at naming and structures and all of those sort of things. Then we looked at properties, boiling point, melting point, all of that sort of thing and how it's affected by the different types of molecules. And today we're going to look at reactions. So this is quite a theory. There's lots of theory in this one, okay, but you guys can manage it. I know you can. You've stuck with me so far. So the first thing we're going to need to do is to make sure you understand some of the terms. So let me just show you the terms we're going to be discussing. So you need to be discussing combustion, what is an addition reaction, a substitution reaction, an elimination reaction, esterification, and cracking. Okay, those are really important terms. So what I'm going to do is I'm going to give you 2 minutes, and in that time I want you to quickly discuss what you understand about those terms. Okay, get through as many as you can. So you've got 2 minutes, and you're going to start now. So, grade 12s, I hope you did okay with that. And now what we're going to do is, before I go through all those definitions, we're going to go through them little by little and see how you did. So we're going to start with combustion. Now, combustion, you really have done combustion before. You've done it in grade 10 and 11. It's just a little bit, we just adding a little bit of extra to this for grade 12. And combustion is when we burn something in oxygen. So actually, it's a redox reaction. And any alkane, any alkane, doesn't matter its size, when it burns in oxygen, will always give us carbon dioxide and water if there is sufficient oxygen. Okay, now this is quite important, and that's why we've got the 2 diagrams here, and you can see the difference in the color of the flame. It's actually quite interesting. On the left-hand side, over here, this incomplete combustion is because we don't have enough oxygen. So there's a very low oxygen supply. And what happens is, not only is the color a different the flame a different color, but we also only get carbon monoxide. And that's a problem with cars, because a lot of the times inside the car's engine and with the exhaust pipe and all the rest of it, the fuel, the petrol, isn't getting enough oxygen. Because it doesn't get enough oxygen, there's incomplete combustion, which creates carbon monoxide. And that's the dangerous stuff that comes out the back of the car. Yes, carbon dioxide is also dangerous. Plants can use it though, okay? So it's not as dangerous. And carbon monoxide is incredibly toxic, incredibly poisonous. So that's a problem with cars, because we create carbon monoxide. If we have sufficient oxygen, we will always get carbon dioxide and water, without exception. Now, delta H is negative. Now, you learned that in grade 11. That means it is exothermic. It gives off lots and lots and lots of heat, which is why alkanes are very good fuels. Grade 12 is a little bit of a tip here for you. If you get asked to write an equation, so butane plus oxygen gives you carbon dioxide and water, you are going to have to balance it. Now, I know that balancing sometimes can take forever. If you struggle with balancing equations, please don't waste 20 minutes of your exam. Get yourself in a big tiz because you didn't balance the equation when it's only worth 1 mark. So rather know that you write the butane, the oxygen, carbon dioxide, and water, and you're fine. You move on. Okay, so we're fine with it. So that's combustion. Now, addition reactions. Addition reactions are incredibly important. Addition reactions only happen with unsaturated hydrocarbons. In other words, there needs to be a double bond between 2 carbons, or there needs to be a triple bond between 2 carbons. That is the only way it can happen, because what we're going to do is we're going to take other atoms or groups of atoms and add them to the hydrocarbon that we started off with. So we can break the double triple bond and add extra atoms. Now, there's different types of addition reactions. The first one is hydrohalogenation. Okay, it sounds a lot more complicated than it is, but what that means is I add in a hydrogen halide, like say, for example, HBr. Okay, hydrogen bromide. That means I'm going to create a haloalkane. So whatever my alkene was, I'm going to get bromo and whatever it was. So if I had butene to start off with, I'm going to end up with bromobutene. Butane, not butene, because we're breaking the bonds. The next one is halogenation. Now, halogenation is quite important because halogenation, we just add in a halogen. That could be something like, say, chlorine. What's really important here is that we end up with a dihalogen in the name, because both chlorine atoms will come onto my haloalkane. All right, so they'll both go on. So because we've got space, they're both gone, okay? But halogenation is a very, 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 very important test for unsaturation, or a test for saturation, depending on how you look at it. Your alkenes and alkynes are very reactive because of the double and the triple bond. So an addition reaction takes less energy than a substitution reaction. So that means that when I add in compounds, because I'm not removing something to add something else in, it can happen faster. Now with bromine, what happens here is the bromine comes along, and it's normally bromine water, and it's brown in color. We add it to our clear hydrocarbon, we get it goes brown, and then we wait for it to turn clear again. The faster it goes clear, the more unsaturated it is. And also, for the test of unsaturation, you don't need to help it, so you don't need heat or sunlight, whereas with a substitution reaction with an alkane, you absolutely need heat and sunlight. Otherwise, it just doesn't take place fast enough. And in fact, this used to be one of the pracs, and it was very frustrating because if you did it on a cold day, it would take forever. And with the hydrocarbons, they tend to evaporate quite quickly. So my classroom would smell terrible for a while. Then the next one is hydration. Now, hydration is hopefully a word you've seen. Hydration has to do with water. So when I hydrate an alkene, I break the bond. The water, remember, is H2O. The water is going to break up into H plus and OH minus. This OH minus creates the alcohol. So by hydrating an alkene, I can create an alcohol. This is not how we create alcohol for drinking. Okay, that like when we're looking at grapes and whatnot when we make wine. That's a fermentation process. That's a different process altogether. But in industry, if we make an industrial alcohol or say surgical spirits or something like that that you use in the medical field, it can be made through hydrating an alkene. Then, of course, we get hydrogenation, and that name comes from hydrogen. Okay, so it comes from the fact that we add in hydrogen to it. Okay, and now I want to show you what's actually happening. This is actually very cool. So here we have hydrogen being added to an alkane. Oh, no, I went back to the top of the page because I can. So what's going to happen here is this double bond is going to break. And the double bond breaks and moves a little bit. And this double bond breaks. Now, even before we do anything else, you guys can see now that both those carbons are missing a friend. Carbon has to have 4 friends. It's one of those things. And at the moment, it only has 3. So what happens is the hydrogen here breaks. And now it comes along and it bonds over here. Now, this isn't exactly how you would write it, but it comes along and says, hello, hydrogen. Hello, carbon. We're all nice friends. This one does the same. Goes over here. Goes, oh, look, let's do this. Now, obviously, we know that we would draw it all nicely out, and when you draw this, you would end up with, you draw it like this, okay, because we've got to draw it properly, but you get the idea that we're breaking the double bond. Now, whether it's hydrogenation, hydrohalogenation, whatever the case may be, it's the same process. We're breaking the double bond, and we're adding in singles. If it's a triple bond, all we're doing is we break one of the bonds at a time, and then we end up with an alkene. Okay, it's the only difference. Now, that takes us to substitution. Now, substitution reactions can only happen with saturated hydrocarbons. In other words, carbons with only single bonds between the carbon atoms. And in a substitution reaction, we're doing exactly what the name suggests. We're taking one hydrogen off, and we're adding it, or we're taking one atom or group of atoms off, and we're substituting another group. So we're changing the functional group. So when we add an alkane and a halogen together, we'll end up with a haloalkane and a hydrogen halide. Substitution gives me 2 products. Addition only gives me 1. Substitution gives me 2. Because even though, say for example, this is bromine, I can only substitute 1 atom at a time, not 2. Which is why when the hydrogen comes off the alkane, it's got to go somewhere, which is to the bromine, okay, why we get hydrogen bromide. If we take an alcohol and we add a hydrogen halide, so what happens with the alcohol, we have the OH, and let's say this is hydrogen, I don't know, chloride for a change. What's going to happen here is the chlorine comes along and it substitutes itself with the H, with the hydrogen, with the OH, with the hydroxyl. That means this alkane, haloalkane, will have the chlorine attached to it, and this OH bonds with that hydrogen, and that creates the water. Okay, so that's where we get the water from. Haloalkane and a base. Now, please be careful here. There's an important condition here. Number 1, this must be a dilute, strong base. Okay, very, very important, and this is what we call a moderate or a mild heat. Okay, you can't just say heat. That's really, really important. And what's going to happen here is this is going to break up, okay? The OH is going to take the halogen from the haloalkane. That creates my hydrogen halide, and then the OH goes onto the alkane part of it and creates the alcohol, all right? And last but not least, before we take a break, elimination reactions. Now, elimination reactions are the opposite to addition. So, addition takes unsaturated hydrocarbons and creates saturated hydrocarbons. Elimination takes saturated hydrocarbons and creates unsaturated, it's the opposite. So, in elimination, I'm going to take atoms off my compound, but I'm not going to replace it with something else. I'm going to take it away. I'm eliminating it. And because my carbon atom has to have 4 bonds, as soon as I remove something from 2 carbons, they're going to come together and form a double or a triple bond, whatever the case may be. We also have elimination reactions because we take bigger molecules. It's not cracking. We'll get to that later. We're taking bigger molecules and we make smaller molecules. Elimination must also give me 2 products at least. So, first one is dehydrohalogenation. Now watch here. If you look at the first part of that, that looks the same as the substitution reaction. The conditions are really important. Number 1, that must be concentrated. Okay, and number 2, this must be what we call a high heat. It's got to be very hot. It takes a lot more energy to do an elimination reaction. Okay? Dehydration with an alcohol. Dehydration because we're going to remove an OH and an H, and together they create water. When you lose water, you get dehydrated. So we take water off the alcohol, becomes dehydrated, okay? And that, wow, got there just in time, and we've done a lot, okay? And knowing these reactions is really important. The best way to really learn them is to do problems. So we're going to take a short break, grade 12s, and when we come back, we're going to see how much you actually know. So I'll see you in a couple of minutes. Welcome back, grade 12s, and now it's time to see how much we actually know. So I have a question here for you, and I want you to look at it quickly. And it says most organic compounds undergo substitution or addition or elimination. So we're giving you an idea of where we're going to produce a variety of organic compounds. So here are some incomplete organic reactions as represented below. Now we have several questions that I want you to do, which are over here, okay? And I'm going to give you 3 minutes to work through them. You probably won't get through all the questions, but get through as many as you can. All right, I'll put the reactions back on the board for about 30 seconds or so, so you can get the reactions, and then we'll go from there, all right? So I'm going to give you 3 minutes, and we'll see how far you get, okay? So here's the beginning of the question. There, it's coming. There's the beginning of the question, and that's the important information, so we're going to start from now. So grade 12s, how do you think you did? Probably not as well as you would like, but that's okay. Now I want to show you a really important skill. So when we go to the question, so here's the question, and I'm not even going to look at question 1, 2, 3, whatever they're asking. It says most organic compounds, I said that, and then we've got the incomplete organic reaction. So now I look at this and I go, because in the beginning of the question they mentioned addition, substitution, elimination, I'm going to be asked about that. Now, obviously here I can be asked to name, to draw, all of that sort of thing. But more than likely, because these are incomplete, I'm going to be asked to complete them and to identify what sort of reactions they are, okay? So that's what I do before I even look at the questions. And I go, fine. So I start over here and I go, well, I have a double bond. I'm adding water to it. So that means I'm going to break the double bond. So we're going to have a CH3. It's going to become that's going to stay CH2. Then I know this double bond's going to break. And here's where things get a little bit tricky, because now I've got to decide, well, those two hydrogens will stay there. And because it's CH and this one will stay with its one hydrogen, because it's H2O, that means it's going to break up into hydrogen and OH. So that means I'm going to create an alcohol. This is a hydration reaction, okay? And it means that it's also an addition reaction. So I know this is addition, and the double bond tells me that. The water tells me it's going to be hydration. More than likely, I'm going to have to decide where it goes. So now we use, remember, it's Markovnikov's rule, and the best way to, you don't need to know the name of the scientist, it was a Russian. Best way to remember this is what like I tell my kids, hydrogen's a bit of a snob. Hydrogen, when it comes off the water, only likes to be with other hydrogens. Okay, it's very rude, okay, and it's very much a snob. So when it looks at the two carbons and it goes, okay, so which carbon do I need to go with? It goes, you know what? In its nice snobby voice, it goes, I'm going to go to the carbon that has already got lots of hydrogen friends, because then I know it's good enough. So this hydrogen goes over here, and hopefully you guys have stopped laughing long enough to actually be with me and remember where I'm going. Sure. So the OH goes over there, okay? So we're creating a secondary alcohol, but that's really important. So we've got the first one. We have a double bond over here, so that's also going to be an addition reaction. The hydrogen bromide's going to break up. It's going to break into hydrogen and bromine, and once again we've got to decide where the hydrogen will go, and the hydrogen, being the snob that it is, will go onto the CH2, and the bromine will come there. The next one, now look at what we've got. We've got an alcohol, but it's not been added to anything. This makes this an elimination reaction, because what's going to happen, I'm adding sulfuric acid to it. Sulfuric acid is actually a dehydrating agent. So what's going to happen is it's going to take the oxygen off, the OH off, and then we're going to have to decide where it comes off from, okay? And it's the opposite to the Markovnikov's rule. And what will happen here is actually the OH will come off, and the hydrogen that needs to come off with it will be from this carbon, because hydrogen likes to be with friends of its same kind. So this carbon's not going to give up its hydrogens very easily. Okay, so we know we've got two addition reactions and we've got an elimination reaction. So now we go and we say, fine, let's look at the questions. First of all, it says, name the type of reaction represented by reaction 3. Oh, look at that. Didn't we just name that? We said, yes, it's elimination. So we don't even have to think about it. It's an elimination reaction. So there we go. Now, reaction 1 and 2 are both examples of addition reaction. Yes, we got it right. Name the type of addition. So we go back and we say, well, in number 1, I'm adding water, which makes it hydration. In number 2, I'm adding a hydrogen and a bromine. So for number 1, it's hydration. And for number 2, we're adding a halogen, so it's halo. And then we're adding a hydrogen, hydrogenation. Okay, there we go. We're all happy. Then write down the structural formulae and IUPAC name of the major product formed. And you know what? Now we don't even have to think twice about it, because we go back and we look, well, actually we've worked it out already. Do you see? We decided where the OH goes. We decided where the H goes. So all we have to do is, we had it in front of us, so we're going to go, fine. I would have had CH3. Now we're going to write it all nice and neatly, because remember, it's important that your marker can read it. So there we go. Those two stayed the same. Then we decided that the OH was going to go on this one, and the hydrogen goes over here. So that's great. Now we need to name it. So it's 1, 2, 3, 4. 4 means bute. That makes it butanol, but remember the OH could be on number 1 or number 2. So we're going to number it from the right-hand side. So it's going to be 1, 2. So this makes this butan, okay, 2-ol. Okay, please be careful. I know sometimes my A's and O's look the same, but be careful if you write ol like that, because it can look a little bit like L, which makes it an aldehyde, and you'll get marked wrong. So rather overemphasize the O and the L just to make sure you don't lose any marks because they can't read your handwriting, okay? Then, reaction 1 only takes place in the presence of a catalyst. Write down the formula of the catalyst used. So we look at it, and it's H2O. Here are the conditions. Now, I haven't spent a lot of time on the conditions because we've got to do a lot of stuff in, but you need to go look back in your textbooks, okay? They will all be there, but the conditions are incredibly important, okay? So, for example, the hydrogenation of an alkene, we use platinum or nickel or palladium as our catalyst, okay? But the conditions are important. Now, here, with hydration, it's the opposite to elimination. Actually, it's quite funny because elimination uses sulfuric acid, and so does hydration, H2SO4. Okay, that's very cool. So now, write down the structural formula, and IUPAC name of the major product formed in reaction 2. We've done it. Can you see why we work through this? And yes, we take some time to do it, but rather take 5-10 minutes to work through the question before you actually get to the questions, because now it takes us a lot less time, because now we know where the bromine needs to go and we know where the hydrogen needs to go. All we have to do is take our little scribbles, which are now gone, and we're going to go, well, we've got CH3 and CH that was there, and we recognize that the bromine would go on this one, and we had a CH over here, and then we have a CH. Okay, so now we've got the structure. Now we've got to name it. This one's not going to be pretty because there's a couple of things. So we go, fine, I've got to name where that is. I've got to name where the methyl group is, and we've got 1, 2, 3, 4. So I know it's bute. Okay, and it's all single bonds, so I know I'm just going to write it roughly over here. So this is just my working out, so I know it's going to be butane. Then I've got to decide where they are, and I've got a bromine and a methyl group, so I know it's going to be bromo. That's got to come first, and I know it's going to have a methyl group, because remember, it's got to be in alphabetical order. And we go 1, 2, 3. So if a number from the left, it goes on to number 3, a little high. Number from the right, we go 1, 2. 2 is good, so it'll be 2. And a 2, and you realize that is just ridiculously untidy. So when you write it down, you go 2. So I'm going to write it nicely. 2 bromo, 2 methyl, butane. See, when I try, I can actually write neatly. My learners moan at me all the time. Anyway, then it says, to which homologous series, hate that word, series does the organic product formed in reaction 3 belong? Now, reaction 3 was the elimination reaction. We're taking the OH off. Elimination means I'm going to go from single to double bonds, which means if I'm creating a double bond, it's going to belong to the alkenes. Now, from here, there's all sorts of things they could have asked you for the product, all sorts of things they could have asked you for this one. All right, so don't get too stressed about that, because this was just one question. It's all right, we've got there, okay? So, little bit more theory before I let you go for a small break. We need to look at esterification. NB. Extremely important. I promise you're going to get esterification. It's also one of your pracs. If you take an alcohol, add a carboxylic acid, use concentrated sulfuric acid as a catalyst, you will get an ester in water. What happens is the OH from the alcohol comes with, so remember then this is the rest of the carbon group, the Carboxylic acid looks like that. Okay, and what happens here is this hydrogen comes off, bonds with that OH from the acid. Okay, that creates the water. That leaves space for the ester bond. So whatever carbons were here, then we have the O, then we have the C, then we have the double bond, and then we have the rest. Okay? The nice thing about esterification is you name it from the alcohol and the carboxylic acid. So whatever alcohol you had, so say you had propanol, that becomes propyl, first part of the name. If I had butanoic acid, then it becomes butanoate, the butanated. Okay, so the name comes from the alcohol and the acid that's involved, and we always break it over there. And don't forget, we always get water. Okay, we've got one more general reaction to do. Then I'm going to look up a couple more questions, but I do think I can hear the brains are starting to get a little overheated, so I'm going to give you a small break, and then when we come back, we'll quickly finish this off. So I'll see you in a couple of minutes. Welcome back, grade 12s. During the break, I realized I forgot one extra thing for the esterification that's really important. Besides the concentrated sulfuric acid, it must also be heated. Okay? Now be careful, we don't heat this directly. The alcohol in this mixture is incredibly flammable. So if you heat it directly over a flame and your test tube breaks, then it's very dangerous. So what we actually do is we put the alcohol and carboxylic acid in a test tube into a beaker with water, and we heat the water. It's a safety measure. We put it in a water bath to make it easier for us, okay? So, last one we're going to do, and I haven't touched on polymerization. We just don't have time, but you must go and look at it, okay? Now, cracking is like a type of elimination, but what happens with cracking is we take really big hydrocarbons with 100, 200, 300, whatever carbons in it. So they're these long molecules which are actually fairly useless, basically. And through either thermal or catalytic cracking, we break it up into lots of little ones. And that's what we do with crude oil. So when they mine crude oil, either at the sea or in North Africa or wherever it is, that crude oil needs to be refined, and by refining it, we crack it, and by cracking it, we break it up, okay, into more useful compounds. Now, there's two ways to do this. The first way is by thermal cracking, and thermal cracking is exactly what it sounds like. Thermal means heat. So thermal cracking means that I put it under very high temperatures, okay, so we have it at a very high temperature, and we also use relatively high pressure. The problem with thermal cracking is that we have to use such high temperatures and pressures, which means that it's a little more dangerous, it's not as easy to control, and we don't use a catalyst. That doesn't really make it any cheaper because it's expensive for pressure and temperature, okay? The more common way of cracking now is catalytic cracking. And what that means is because we use a catalyst, okay, and you don't need to know what the catalyst is, it's normally a zeolite. You don't need to know what the catalyst is because it's a very complicated molecule. Using a catalyst means that I can have the same concept of breaking the molecule up, but I don't need to use the high temperatures and I don't need to use the high pressures, which makes it safer. Okay, so cracking means, just as an example, we've got 1, 2, 3, 4, 5, 6, let's make this 7. Okay, and I'm not going to draw the hydrogens. So here I have heptane, and now we crack it. And whenever cracking happens, what happens is you must get at least one alkene. So they'll say to you in an exam, for example, that one of the products formed is butane. Okay, and then they say to you, what is the other product formed? So now this looks quite complicated. You go, how are we supposed to know? Because there's hundreds of products, but it's actually easy. You're not going to get too bent out of shape. So we had 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, it is 7, I think. Or it is. I'm having a bad counting day apparently. So we had 7, and we've used 4 already. Okay, so if 1, 2, 3, 4 carbons have already been used, so I know my last compound is going to have 3. So we're doing okay so far. Because it was butane, we used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon hydrogen. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That leaves me with 1, 2, 3, 4, 5, 6 that I need to put around here. So we go, okay, normally we'd go 1, 2, 3, 4, 5, 6. Okay, we have a problem. Can you see the problem? Carbon doesn't have enough friends, but we don't have any more hydrogens. So we go, fine, let's take that one away over here. So we're going to go back to the 3, and we're going to go, well, I had 3. Okay, let's put 1 there, so that's 4. Let's put a double bond over there, and then that's 5, and that's 6. Look at that. There's my second product, otherwise known as propene. So you have to work it out. It's not great, but it's all right. It's not so bad. So the worst they can do with a cracking is they can ask you what the second product would be. They can't ask you to determine from a single compound what all the products will be without giving you some idea of what they are. Okay, because this is only one way that heptane could crack. And heptane only has 7. As soon as you get to 8 or 9 or 10 or 11 or 12 or 15 carbons, there is ridiculous amounts of numbers of compounds that you can get, and you aren't expected to know that. Okay, so let's see if you're ready to tackle a problem. So here I have a problem for you, and I'm going to give you 2 minutes, okay, to look at it. So let's just look at the first part of the question together, and it says hexanoic acid is responsible for the unique odor associated with goats. I'm not really sure what that is, but let's just go with it. When it reacts with an alcohol, ethyl hexanoate, which is used commercially as a fruit flavor, is formed. Learner set up the apparatus to prepare the ethyl ethanoate in the lab. So here we have hexanoate and an unknown alcohol, beaker, in a water bath, off we go. Okay? So you got an idea of what the information is that we're giving you. I'm now going to show you the questions. I'm going to give you 2 minutes, and then we'll see how far you get. Okay, so you ready, grade 12s? And we're going to start your 2 minutes now. So how did we do, grade 12s? Probably screaming at me going, there wasn't enough time. It's all right. You're starting to get there. So let's look at the question. So here we have that again. And I could tell you straight away that because in this question they had alcohol X I can almost guarantee you they're going to ask you to name it. So even before we start the question, let's look at it. And I can get the name of the alcohol from this because it's ethyl hexanoate. Now, from what I just told you, the anoate part comes from the acid, which was hexanoic acid. So the ethyl means that comes from the alcohol, which means it has to have been ethanol. Don't even have to think about it, okay? First question. Write down the IUPAC name of alcohol X. Oh, look at that. We've done it. So it's ethanol. Brilliant. What is the role of the sulfuric acid in the above reaction? Well, I told you earlier, it is a catalyst. Brilliant. So we're all nicely done. Now it says, use the structural formulae to write down a balanced equation for the preparation of ethyl hexanoate. Now here it's about being nice and neat, and I'm probably going to have to do it over 2 lines because it's just not quite right enough for me here, all right? So we start with the ethyl. That means I'm using ethanol. So ethyl means ethanol. Okay, so there's my ethanol. And even though it says balanced, you never ever have to add in any numbers to this. So there's the ethyl. Hexanoate means hexanoic acid. So that means hex is 6. So 1, 2, 3, 4, 5, 6. And we're going to have 8. Sorry. Like I said, I didn't think there's the acid part of it. Now we put in all our hydrogens. Okay, and I know it gets boring, but you must put in all the hydrogens. So there we go. Don't put in hydrogen in the last one because then the carbon's got too many friends. And so now we make ethyl. So now we need the ethyl hexanoate formula. So that's 1, 2. Then we have the oxygen. Then we're going to have the carbon with the double bond oxygen from the hexanoate, but there's still got to be 6 carbons. So that's the first, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Great. Now let's add in all the hydrogens. Don't put any hydrogens on the carbon with the double bond oxygen, otherwise it's got too many friends. Okay. I know you can't really have too many friends, but you know, in organic chemistry, carbon is very fussy. You can only have 4, no more, no less. Otherwise it gets a little nervous. Okay, but we're not done. We're not done. Don't forget that we also create water. And the water must be drawn out structurally as well. So when they ask you for a reaction that's with structural formulae, they mean every compound that has covalent bonds, you must show the covalent bonds. Okay, there is no option here. You can't write H2O. You must show it, but you never show the bonds when it comes to something like sodium hydroxide, for example, because that's ionic. Okay? Good. Now it says, give a reason why the test tube and its contents are heated over in a water bath and not directly over a flame. Well, I said this to you earlier. We heat it in a water bath because alcohol is flammable. All right? That means this is a safety measure. It's a safety measure. Okay, it's to make it safer for us. Then, write down one use of esters in the food manufacturing industry. There's lots of them, but because I said food manufacturing, you can't say it's used to make perfumes. Okay, I don't particularly enjoy eating perfumes. Ladies, if you've ever sprayed perfume in your mouth, even deodorant, by accident, it's horrible, okay? So we don't use that. It's not the food industry. What they mean by this is for artificial flavoring. Artificial flavorings, okay? Whether it be creating vanilla essence or raspberry essence, or whether it be the flavoring they put into chocolates or the flavoring they put into drinks and cold drinks, it's all part of that. Okay, so now what I want to do, and we are going to run out of time, but I want to show you something. This is the next question. I don't have time to let you do it on your own first, but this is very typical of the type of question you can get in your exam. And what happens here is you guys look at this and go, oh, I don't know what to do. Don't panic. I want to show you how you work through this. It says, in the flow diagram below, X, Y, and Z represent 3 different types of organic compound reactions. P represents an organic compound, not an inorganic. That's important. So we have on the left-hand side over here, we have a haloalkane. Over here, we have an alkene. And then they give us some clues in that we start on the left-hand side with a haloalkene, which becomes an alkene. The only way that a saturated hydrocarbon can become an unsaturated hydrocarbon is through elimination. So reaction X has to be an elimination reaction. When this comes off, look at what's happened here, is if you compare the left-hand side with the right-hand side, the bromine came off, okay, and so did one of those hydrogens. So over here we end up with hydrogen bromide. But now before you say, but Tracy, more than that came off. No, it didn't. Be careful here. This, let me do it in a different color. I think it'll be easier for you to see. This CH3 is that CH3. This CH3 is that CH3. It rotates because of VSEPR, because of molecular geometry. Okay, so don't worry, it's HBr that came off. We haven't done anything funny. Now, and this is where conditions are so important. With reaction Y, they tell you that we use KOH aqueous, that means dilute, with a mild heat. That means this has to be a substitution reaction. The only thing I can substitute on here is the Br. So the Br is going to come off and I'm going to substitute it with something else. I don't have enough information yet as to what that substitution will be. Because this compound is created by both of these, by the haloalkane and the alkene, the only way the alkene can become a saturated hydrocarbon is for this to be an addition reaction. Now, what that addition reaction is, we don't know yet, because there's lots of things I could do here. My gut feel, and this is just because of my experience, is this is probably going to be an alcohol. Okay? Because I would break that double bond, I would put water here, this would become a hydration reaction, gives me an alcohol, and because of the OH there, it's going to give me an alcohol. Okay, in fact, it will give me an alcohol, I know that. Now when I've worked through all of this, now when I go to the questions and they say, name the type of reaction represented by X, I've done it. Okay, X was the elimination reaction, don't even have to think about it. The 2 conditions for the elimination reaction, well, it's the opposite to the, it's not the opposite, it's different to the substitution. Remember, strong base, high heat. Okay, strong base, high heat. Reaction Y represents a substitution, which I said it was. Write down the structural formula of compound P formed in this reaction. So when we go back here, that OH substitutes the Br. So it's actually not so hard, it's the same thing, but remember, be careful here. When you draw it out, you draw all the hydrogens, okay? And that becomes an OH, straight substitution. Okay, it makes an alcohol. Then they say, apart from the organic reactant, write down the name or formula of the other reactant needed in reaction Z. Oh, wait, look there. Done. Water. And then the last question, type of reaction. Oh, wait, we did that too. Look at that. Addition. Now, I know where I'm going, but I want you to see it took us 3 minutes to go through the question, to look at the paper. It took us a minute and a half to do the answers, which I know I did quickly, so you might have to watch it again. But it's all done, okay? Grade 12s, I have to leave it there for that. Lots of stuff. Well done. Keep studying, and I will see you next time.